Hello students, welcome to Sri Jendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 1 of a unit gravitation. Let's begin with today's class. In this session we are going to discuss a very introductory session about the gravitation. So let's begin. We sometimes observe that all the things in this earth's atmosphere are attracted towards the center of the earth. Why? What makes these things to get attracted towards the center of the earth always? So what would be the answer of this? We must say that it is the gravitational force that always makes things falls in the downward direction. It is the gravitational force which will do this for us. Look at this. If you observe this, that why does an apple fall down instead of going in an upward direction? I'm sure you must have heard the story of this Sir Isaac Newton, that he was sitting under a tree and apple has been fall down, and he thought uh, why this has been moving in the downward direction instead of it can go to the upward direction as well. So another question, it's why do the raindrops fall on the earth? So all these questions are having an answer in the gravitation. We understand that there is a certain forces is acting which makes this to move down. So let's discuss from very basics. In basically we have a fundamental forces, and we have four fundamental forces. They are the gravitational forces, strong nuclear forces, weak nuclear forces, and electromagnetic forces. If you have gone through the physical world, they have a detailed applications and detailed notes on this. Yes. In this unit you are going to discuss about the gravitational force. This strong nuclear force and weak nuclear force, this are the part of the modern physics that will cover in class 12. And this electromagnetic force, again this is the unit 12. This is the unit 12. It's that means the class 12. Sorry, it is the part of the class 12. Certain units of class 12 covers this. Yes. So even if you have not gone through the physical world, not an issue, we are going to cover this topics in the particular units of the class 12. Yes. So but these are the fundamental forces in nature. When I say that fundamental forces, what I mean is that all other forces are the derived applications of these forces. We know, and now we understand the so many forces. We understand the tension force, friction force, normal force, pseudo force, centrifugal force, and whatnot. But all these forces are part of this forces, are derived part of this applications only. I hope you understand. Do you? Do you understand this? Great. So now let's look at the some of the examples of the gravitational force. We can say that any satellite that we have launched from the earth, that we call it's an artificial satellites, yes, that can move around the earth due to this forces. We can say that this is just the image of a launching of a satellites. Yes, that it was just ready to launch. Even this can move, and the payload will come back to the earth. Why? Because gravitational force is there. You can see that let's say this is moon, and moon is rotating around this earth. Why? Because of or due to gravitational force. Here in this image you can see that earth is rotating around the sun, while this moon is rotating around the earth. This is possible. Why? Because of because of gravitational force itself. So gravitational force has a wide range of applications, but its basics are same, that it is going to be always attractive force in nature. Gravitational force is always attractive force in nature. It is going to attract every time. Yes, and that have many different applications. So before we begin with the gravitational force, first we need to understand Kepler's laws for the planetary motion. So let's begin with the Kepler's laws of planetary motion. Basically, a scientist named as a Kepler has given us the laws which can which can help us to understand the planetary motion. And he has given the third law. It's a Kepler's first law, or we can say law of orbits. Kepler's second law, or we can say it's a law of areas. Kepler's third law, or we can say law of the time periods. So basically, he has given this three laws, um, and which is correct for the planetary motion, as well as this rule. This all laws are applicable. This all laws are applicable to the artificial satellites too. So will this will make us understand that how gravitational force will work and how we can understand it correctly. So let's begin with the Kepler's law. So let's begin. It's a Kepler's law of planetary motion. So before we start the Kepler's law, let us understand some concepts of the ellipse, because every time we are going to deal with this when we are talking about the motion of a planets or motion of the satellites around its central body. So let's understood what ellipse is. This curvature or this diagram you see is the diagram of ellipse. This is how it look alike. It is the ellipse that you understand. Ellipse will be having a two axis, one having the larger size. Look at this, from here to here, one having the larger size from here to here. It is the major axis, and the one from here to here, it's a minor axis. So basically two axis would be there. One axis having a higher size is the major axis, and one would be the shorter than that is the minor axis. Now now let's understand that this you can say from here to this, probably you can understood this as a central point, that this can be considered as semi major axis, and this smaller part, this can be considered as semi minor axis. So this is semi major axis, this is semi minor axis. Next, this two points, please understand this very carefully. These 2 points are called as the foci. This and this, it's an f1 and f2. This are two foci. Ellipse always having a two foci, one represented as f1, another represented as f2. So now let's discuss Kepler's first law, or we can say it's a law of orbits. What is it? It says that each and every planet moves around the sun in an elliptical orbit, while while sun would be at one of the foci. It says that let's understand that this is ellipse. um, yes, now it is visible. So it says that every planet moves around the sun in an elliptical orbit, while sun would be at one of the foci. This is f1. Here f2 would be there, it's a second foci. So sun would be at one of the foci, and each and every planet are revolving around the sun in an elliptical orbit. I hope this is clear. Is it correct? So look at this may be more clearer. This is the foci 1, and this is the earth. This is the foci 2. Yes. So this is the case when every planet are moving around the sun in an elliptical orbit. I hope this is clear. While sun would be at one of the foci. Yes. So f1 f2 are the foci. A to O, it's a semi major axis, while O to C, it's a semi minor axis. Is it clear? Is it clear? Great. Now let's discuss certain point. Look at this. This is sun, and this is a point which is nearest on this elliptical journey. Sun up. Every planet is moving in this direction, moving in this path. Yes, every planet have its own orbit, but it would be elliptical for sure. So every planet is moving in an orbit like this. There is a certain distance which is nearest to the sun, and that nearest to the sun, that distance which is nearest to the sun, that we call as in perihelion or perigee. It's a distance of the closest approach of the planet with sun is called as the perihelion or perigee. So it is the distance of the closest approach. It is the minimum possible distance of the planet with sun that we call as a perihelion or perigee. Next is the aphelion or apogee. It is the greatest distance. Aphelion or apogee is the greatest distance of the planet from the sun that we call as an aphelion or apogee. This is the farthest point from the sun. Yes, it is the greatest distance of the planet from the sun that we call as an aphelion or apogee. I hope this is clear. Is it is it clear? Great. So now let's look certain quick questions. It's the first law of Kepler's is also known as, yes, it's a law of orbit. Law of period. Yes, it's a third law. Law of area. It's a second law. And law of gravitation. This has been given by Newton, not by Kepler. I hope this is clear. So this is law of Newton, law of gravitation, not by Kepler. Yes, so this would be the correct answer. Second, second, it says that every planet revolves around the sun in an elliptical orbit with sun at one of its foci. That is stated as, this is law of orbit. Yes, Kepler's. We say this as a Kepler's first law. I hope this is clear. Is it is it clear? This is Kepler's first law. Great. Now now let's work for the Kepler's second law of planetary motion. Let's have a look. It says that the radius vector drawn from the sun to any planet sweeps out equal areas in equal intervals of time. It says that the radius vector drawn from the sun to any planet will sweep out equal area in equal interval of time. According to the Kepler, since time taken by the planet is same, their area covered is also the same. So what you can understand is, this is sun which is at one of the foci. Let's understood this is earth. Suppose you have started your stopwatch at here, t is equals to 0, and you have stopped your stopwatch by here, which is t is equals to, let's say, 30 minutes. Now now again you take a different situation. Again you started your clock by here, it's a t is equals to 0 minute, and you have ended it on this, it's a t is equals to 30 minutes. So this is a span of 30 minutes on both the sides. This is a span of 30 minutes on both the sides. So according to the Kepler, he says that if time taken by the planet is same, then their area covered is also the same. That's why this is known as the law of the areas. Yes, great. Now let's look at this. This the law of conservation of angular momentum is valid for any central forces. When I say central forces, I mean it is the force which acts between the center of the first body to the center of the another body. A central force is that force on a planet which is along the vector, yes, joining the sun and the planet. So now it is just the statement that if time taken by the planet is same, their area covered should be also the same. Let's prove this, that how this is possible. Let's have a look. Suppose we understood that a planet moves in an elliptical orbit, let's say from position A to position B in time frame of delta t. In this situation, the area swept by the position vector r is equal to the area of the triangular region. Look at this. This is from A to B. This is the triangular area that it has covered. So when I write the area vector of this, it's a delta A is equals to 1 by 2 area of a triangle. It's a half into base into height. Yes, that is what we are going. It's a r delta theta multiplied by r. It's a 1 by 2 into r delta theta. So while I write r into r delta theta, it's a 1 by 2 into r square delta theta. I hope this is clear. So this is equals to, let's divide it with respect to time. It's a delta A divided by delta t. That we can write it's a 1 by 2 r square into delta theta by delta t. But I understand that delta theta by delta t, it is the omega. Delta theta by delta t, it's an omega. So let's replace this and get this done. It's an delta A by delta t, that is equals to delta A by delta t, that is equals to 1 by 2 into r square into omega. I hope this is clear. Is it? So if I get this, it's r square omega. The angular momentum of the planet of mass m could be written as L is equals to mr square omega. How this is arrived? It's an L is equals to mvr. If I replace v by r omega, it's an m r omega into r. So this is m r into r. It's an r square into omega. So this is m into r square into omega. And if this is the case, omega could be replaced by L by mr square. So if I replace this now, delta A by T, I have this relation. It's a 1 by 2 into r square into omega. Then I can write it's a delta A by delta T. It's a 1 by 2 r square into omega. Omega could be replaced by L by mr square. This mr square and this mr square could be gone, and this could be written as L by 2m. So here it is the case that if delta A and delta T is same, if delta A and delta T is same, it was just the statement that if time if time taken by the planet to travel is the same, then area must be the same. So if delta A by delta T is a constant, then L, angular momentum L, must be a constant, and this is dA by dt is equals to constant. This dA by dt, it's an area divided by time that we call as an areal velocity. Please remember this is areal velocity. Even it is constant because I understand that L is constant, and while moving on the journey, we understand that even the velocity mass is going to be conserved. So L is constant, and if L is constant, it means areal velocity is also constant. I hope you understand this very well. Is it any doubts up till now? Is there anything? Is there anything? Are you sure? Great. Now let's discuss certain very logical aspects. So now, what do we understand is that the speed of the earth more at perihelion than the aphelion. Is it so? Or it would be the same? So what you need to do is, let's write this angular momentum as LA. This is LA. And let's write the momentum, angular momentum at the perihelion, as an LP. Now we understand that angular momentum is constant, and if it is constant, then I could write it's an LP is equals to LA. While I'm writing this LP is equals to LA, I understand that this M and this M has been cancelled. So VPRP is equals to VARA. That means V is inversely proportional to the distance. Now RA, it's an aphelion, is the farthest distance from the sun, while the RP, it is the nearest, it is the closest approach of the planet with the sun. So RA is greater than RP, and if RA is greater than RP, that means velocity at aphelion would be less than the velocity at the perihelion. That means the speed of the earth at perihelion is more than at aphelion. While I say speed of the Earth at perihelion is more than at aphelion, I even say this. It's a kinetic energy at A. Its kinetic energy at aphelion is less than the kinetic energy at perihelion. Perihelion probably contains the maximum possible kinetic energy of the sun, of the planet, sorry, while revolving around the sun. I hope this is clear. Is it is it clear? Are you sure? Are you sure? Let's again look at the quick questions. Which law states that the line joining the sun and the earth sweeps out equal areas in equal intervals of time? Yes, it's a Kepler's second law. This would be the correct answer. Next, next, it says that the motion of the planets in the solar system is an example of conservation of angular momentum. Yes, all the planets, they are revolving around the sun. They will follow the conservation of angular momentum. This is true for every planet. I hope this is clear. Is it clear? Is it? Any doubts? Is there anything? No? Great. So now let's understand ellipse in more better way. This is ellipse. This is the semi major axis and this is the minor axis. This would be one of the foci that we call as an f1. This would be the another foci that we call as an f2. Yes. Now now if I write down the coordinates of this, it's a 0 comma 0. Coordinates of this, it's a minus of ae comma 0, while this distance, a distance of semi major axis is a. So if this is a, this is for a as well. I hope this is clear. Now this is f1, this is f2, this is minus a comma 0, this foci is at plus a comma 0. Now if I write down this distance, this is rp, that we call this point as the perihelion, this point as the aphelion. So this distance is rp, while this distance, a distance of the farthest point from the sun, this is, let's call as an ra. This is the ra aphelion. So now the situation is exactly what rp is. What would be the value of its rp? So what I understand is this complete distance is a, and this much is only a into a. So I should write it as an a minus of ae, which should be written as a into bracket 1 minus e. Now this is the distance of the perihelion. What about the aphelion? Let's have a look. So ra, that would be equals to ra, sun would be here. This is the location of the sun, and when sun would be at here, this is the complete distance a, and this would be the distance ae. This is equals to a plus ae. So this would be written as a into bracket 1 plus e. This is the aphelion. I hope this is clear. So do you understand aphelion, perihelion? Do you understand this? Have you? Have you understood this? That what is aphelion, what is perihelion? Are you sure? Is it clear? Is it? Great. Now, so if I compare the if I compare the velocities and kinetic energies at these two situations, let's have a look. This is the ellipse. This is this major axis. This is the minor axis. This was the foci where sun is situated. Let's call this foci 1. This is foci 2, and this distance as perihelion, and this distance as RA. It's an aphelion. Yes, and we have the relation that R aphelion is A into bracket 1 plus E. R perihelion, perihelion that we call as the A into bracket 1 minus E. We understood that this is the location of perihelion, this is the location of aphelion. Angular momentum at perihelion and angular momentum at aphelion would be the same. When angular momentums are same, it's an m into vp into rp. This is equals to m va ra. This mass could be cancelled out, so it's a vp by va, that would be equals to ra by rp. I hope this is clear. Yes, so this vp by va, this is equals to ra. Ra could be written as a into bracket 1 plus e, and vp, it's an a into bracket 1 minus e. So this has been cancelled. It's a vp by va, that would be equals to 1 plus e upon 1 minus e. Does it clear? Does it clear? Are you sure? Are you sure? Their kinetic energies. What about their kinetic energies? This is just the ratio of vp is to va. So their kinetic energy at perihelion to the kinetic energy at aphelion, it's a half into m into vp square divided by 1 by 2 into m into va square. So when this is the situation, this 1 by 2 has been cancelled, this m and has been cancelled. This is vp square divided by va square, and while I write it's a vp square by va square, it's a 1 plus e whole square divided by 1 minus e whole square. This is kinetic energy at perihelion to the kinetic energy at aphelion. This is the ratio of the kinetic energies. I hope this is clear. Is it clear? Is it? Is it? Are you sure? If I want to find out the ratio of omegas, if I want to find out the ratios of the omega, I understand that La is equals to Lp. This could be written as mva ra. This is mvp rp. This m has gone. V could be replaced by r omega. So this Va would be Ra omega A into Ra. That would be is equals to Rp omega P Rp. This Ra, this Ra. It is the Ra square into omega A. This is Rp square into omega P. So omega A is to omega P. This is equals to Rp square is to Ra square. I hope this is clear. Now, what is Rp? What is Rp? It's an A into 1 minus A. So, it's an A square into 1 minus E whole square divided by. It's an A square into bracket 1 plus E whole square. This could be the cancel, and this is the ratio of omega. It's an angular velocity at aphelion to the angular velocity at perihelion, which could be given as 1 minus e whole square upon 1 plus e whole square. I hope this is clear. Does it? Does it clearer? Are you sure? Any doubts? Is there anything? Is there anything? Are you sure? Are you? Great. Now, do you understand up till now? Have you? Any doubts up till now? Is there? Is there anything? Is there anything? No? Let's understood one of the logical question that if we move from aphelion to perihelion, what should be the work done? if we move from aphelion to perihelion, what should be the work done? While they understood what would be the work done, they mean to ask is that whether it is a positive or negative. Yes. So this is the situation. This is the location of perihelion. This is the location of aphelion while sun would be at here. Now we understand that. We understand that velocity at perihelion would be greater than velocity at aphelion. Even we have derived this as a kinetic energy at perihelion would be equals to kinetic energy at aphelion. So while saying this, we want to know the kind of a work done, that means positive, negative, or zero. What would be when we move from aphelion from here to here? So this is initial position, this is the final position. So what I understand is work done is equals to change in kinetic energy. And well, when I say work done is equals to change in kinetic energy, I mean to say it's in half mv square at the final position, which is perihelion, minus of half mv square, which is an initial position. As I understand that this kinetic energy would be greater than this one, that means this work done is positive. This work done is positive. I hope this is clear. You can do this by this. Yes, you can easily calculate. You can easily calculate using this situation work done. That is change in kinetic energy. I hope this is clear. Is it? Is it clear? Is it clear? Okay. Now on your own you can do this. If an object moves from perihelion to aphelion, what should be the work done? So this is to be done. This is to be done by yourself. Yes, I hope you understand. It's try yourself. I'm sure you will do this. So, does it clear up till now? Or any doubts? Is there anything? Is there anything? Are you sure? Are you? Okay, great. Now, the next logical question. Next question is that find out torque acting by the sun on planet during its motion in elliptical orbit. So we need to find out the torque acting by the sun on the planet during its motion in elliptical orbit. How will I do this? What can be done? This is ellipse. This is major axis. This is minor axis. Let's understood that this is sun, and let's say this is planet. So now what is torque? When we say it's a torque, it's the position vector cross force acting. It's an r cross f. So if I make a position vector from sun to the planet, it will be in this direction. This is r, and this too, that means the sun and planet have been connected by the gravitational forces. Yes, this two having a masses, and due to their masses they are having a force of attraction. That force is called as the gravitational force. Yes, that force is the gravitational force we are looking for. So this is the central force. So it acts from the center of the first body to center of the second body. So this is r into f into sine theta, while theta would be 180. It's a 180 degree. In this case, when it is 0, its a torque would be 0. I hope this is 0. Yes, so no torque is acting on the planet by the sun due to its planetary motion. Now, one more very important aspect is when torque equals to 0. When torque equals to 0, we understand that torque equals to dl by dt. So this dl by dt would be equals to 0. And when I say dl by dt is 0, when I say dl by dt is 0, so change in momentum is 0. And when change in momentum is 0, when change in momentum is 0, I could write that angular momentum, it's an angular momentum of of planet is conserved. Do you understand this? That angular momentum of the planet is conserved. This is the second proof. This is the second proof that how I can conserve the angular momentum during its planetary motion. Is it clear? Do you understand this? Are you sure? Are you sure? Can this be done? Can it be? Can it be done? Great. One more question. Let's have a look. A situation is something like this. Let's suppose understood that this is the central body at foci 1 and this is foci 2. Let's call it as a sun. Uh, this is pure hypothetical situation. A planet is there and it is moving in this direction with a speed of let's say 100 kilometer per second. Yes. So if this is 100 kilometer per second, they have been asked what is the velocity at this position. They ask what is the velocity at this position. One more thing. They have given that this is let's say the distance between this is 10 into 10 to the power 5 kilometer and this is 30 into 10 to the power 5 kilometer. This is pure hypothetical situation, but what I want a velocity at this point. So what I understand is that let's call this as a first point, this as a second point. Angular momentum at first point is equals to angular momentum at second point. And while I say angular momentum at first point is equals to angular momentum at second point, I must understand that it's an m into v1 into r1. That should be is equals to m into v2 into r2. While this mass and mass could be cancelled out. This v1, it's a 10 into 10 to the power 5 multiplied by it's a velocity, it's an 100 kilometer per second. That is equals to, we don't know about the v2, but my r2 is 30 into 10 to the power 5. So if I try to solve this, this 10 to the power 5, 10 to the power 5 has gone. This is 10 3s are 30. So v2 would be 100 by 3 kilometer per second. It's approximately 33.33 kilometer per second. This is the v2 velocity at this point. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Can you do this? Can it be done? Are you sure? Great. So now do you understand what would be the situation? Do you? Do you completely understand this? Great. Let's let's move to the Kepler's third law. What does it says? Kepler's third law. Let's have a look. It says that the square of the time for a planet to complete one revolution around the sun is directly proportional to the cube of the semi-major axis. Cube of the semi-major, yes, this is semi-major axis of the elliptical orbit, and this is what we call as a t square directly proportional to the r cube, while t square by r cube is equals to constant, where r is the semi-major axis of the elliptical orbit. Yes, again, the square of the time period, the square of the time period is directly proportional to the cube of the semi-major axis of the elliptical orbit. So this is t square, which is directly proportional to the r cube. Does it clear? Does it does it clear? Okay. Now one more thing. When I say t square directly proportional to the r cube, we know that what is the value of r? What is the value of r? How could I do this? So let's have a look. This was the situation. We said this is 0 comma 0 location. This is one of the foci which is minus of a comma 0, and this was the a. Even this was the a. This is the perihelion. This is the aphelion. We know that rp is equals to a minus ae, ra, which is a plus ae. If I add this to, if I add this to, it's an rp plus ra, which is equals to 2a, and this a could be written as rp plus ra by 2. This is the value of semi-major axis. So according to this, according to the Kepler's third law, or the law of periods, I can write this. It's a t square directly proportional to the a cube, and this could be written. This could be written as rp plus ra divided by 2 to the power 3 by 2. It's a t directly proportional to. I hope this is clear. Is it clear? Is it clear? Do you understand this completely? Do you? Are you sure? Great. Let's have certain questions. It says that according to the third law of Kepler, according to the third law of Kepler, it's t square directly proportional to the r cube. Next, according to the Kepler, a satellite, according to the Kepler, a satellite always revolves in an, yes, satellite always revolves in an elliptical orbit. I hope this is clear. Is it? Is it clear? Do you have any doubts? Is there anything? Is there? No? So one more important aspect is that if we assume our orbit as a circular orbit, if we assume our orbit as a circular orbit, because we can assume that as circle is special case of ellipse only. So if your major axis is equals to minor axis, if your major axis and minor axis are same, that means it is not an ellipse, now it's a circle. So we can assume that, what I want to prove is, we can assume that, let's suppose my orbit is circular orbit. If this is the situation, then the thing will be that this is the central body, let's suppose this, and let's say planet is revolving in this. Yes, let's understood that this is the center of the central body, and this is the location of the orbit. On this orbit your satellite is revolving, let's say this as an r. Then you must consider that this distance, when you write the third law in this case it's a t square directly proportional to the r cube, that you understand. But this r is the distance from center of central body to revolving body. Yes, you must be very careful for this. You must be very careful for this. That r is the distance from the center of central body. When I say central body, I mean it is the body around which objects are revolving. We can say that an artificial satellite is there which is revolving around the earth. Then we must understand that earth will behave as a central body and your artificial satellite will behave as the revolving body. Yes. So this is the r is the distance from the center of the central body. One more thing, that many a time to tempt it, what they are given is that they will give you the distance from the surface to the planet. Let's call this as an h. Then we must understand that this is re, and I should write this as a t square directly proportional to the re plus h to the power 3. It's a t square directly proportional to the re plus h to the power 3. That's it. It is as simple as that. You can do this and task will be done. I hope this is clear. Is it clear? Is it? Do you understand this? Please keep this in mind, that this is if the distance of the orbit has been given from the surface of the earth, then you must add the radius of the earth. I hope this is clear. Is it clear? Is it? Great. So now ready for the questions? Let's be with your pen and paper and start doing it. Let's understand that this is the central body and the radius of the central body is r. It is having one of the orbit and this is the second orbit. Yes, these two orbits are there, and the distance from this orbit to this distance, this is 3r. Certain planet is revolving around this, and distance from this to this, it's a 6r, and some other planet is revolving around this. So let's call this first, call this second. They say that if time period of first satellite, if time period of first satellite is, let's say it is a 72 hours, find out time period of of second planet, second satellite, sorry. So how will you do this? How can we done this? We have, according to the third law of the Kepler, it's a t square directly proportional to the r cube, but this r is to be calculated from the center of the earth. So what I write, it's a t2 square divided by t1 square. This is to be equals to r2 cube divided by r1 cube. So this is t2 square divided by t1 square. This is 72 hours, so this would be 72 multiplied by 72. This is equals to r2. So this distance, this is 6r and this is r. So this is equals to 7r cube divide by this is equals to r1 cube. So this is 3r and this is r. This is equals to 4r cube. So if I try to solve this, it's a t2 square is equals to 72r square multiplied by, it's 7 cube divide by 4 cube. So this is 72 square multiplied by, it's an 7 freezer, or 7 to the power cube divided by 4 to the power cube. So this T2 would be equals to 72 into, in the square root of 7 cube to the 4 cube r's. I hope you got this. Do you? Do you understand this? Do you understand this? Yes. Please keep this in mind. Please always keep this in mind, that distance is to be calculated from the center of the earth. Always. This must be clear. This must be clear, that distance is always calculated from the center of the earth. I hope this is clear. Is it clear? Great. Now, ready for the next question? Are you? Let's have a look. That plot the graph for first, it's a t square directly proportional to the r cube, and second, it's a for t versus r. Sorry, I need to plot two graphs. It's a t square versus r cube and t versus r. And I know that relation for this, it's a t square directly proportional to the r cube. So let's begin. First, let me plot this. This is the situation. This is t, this is r. A t is having power 2, r is having power 3, so we always protect one which is having a lesser power. To protect this, I need to curve or slope something like this. Yes, it's a t directly proportional to the r. Now let's plot this. It's a t square versus r cube. This is second and this is first. This is t square, this is r cube. So if I plot for a t square, it is indeed a power of this. If I want to plot for the r cube, it is indeed power of this. So t square is having a power of 1, r cube is having a power of 1. When both are having a power of 1, it must be a straight line. I hope this is clear. Is it clear? Is it? Are you sure? Great. So let's wind it up this session over here. This is all about the introduction to the gravitation, as well as Kepler's laws of planetary motion. Please go through it carefully. We have certain questions from the Kepler's law, and introduction to the gravitation will be in detail we are going to discuss in the next sessions. Thank you. Have a good day. Take care.